Okay, I guess we are ready to start. Hello, good afternoon. Thank you very much for coming. My name is Adam Warski. I come from nearby, from Warsaw. I work at Software Mill remotely for the last 16 years, so a nice round number. So what we will be talking about today is looking at how we can implement local data transformation pipelines, so something that runs on a single machine, as opposed to things like Spark, where we distribute the computation across a number of machines. So here we are staying on a single machine, and we want to transform the data in a streaming fashion. So there was a talk in the morning about another approach to streaming in Java using gatherers. So the idea is slightly similar. However, the Java API focus mainly on transforming collections. Here we will be mainly looking at ways of how we can transform data that has some effects. So various temporal operations, various blocking operations. And the twist here is that we want to use the new features made available by Java 21, that is virtual threads. So with the virtual threads, blocking is once again fine. So something that we've been taught to be afraid of in the asynchronous times, let's say, now is safe to use. So let's see how such an API might look like and what kind of trade-offs we have to do. But before we actually go there, let's maybe take a quick refresher on reactive streams. So there used to be a time when reactive streams were really fashionable, right? Everybody wanted to be reactive, and everybody was talking about being reactive. Now I think the fashion has moved to other things, so it's not that popular, but I think the ideas are still valid. It probably is like just another tool in our toolbox. So I think it's worth exploring what kind of ideas there were and what you might want to keep from the reactive streams approach, right? So if we go to the reactive streams manifesto, as they call it, we can read that reactive streams are a way to govern the exchange of stream of data across an asynchronous boundary, and we want to do it within bounded memory, right? So we want to keep the resources that we use within some constraints. So we don't want to, buffer an infinite amount of elements because that would blow up the whole processing. So that's where the whole idea of back pressure comes in, right? For example. So some use cases where we actually want to use reactive streams, of course, processing streaming data, but also managing concurrency, right? Sometimes you want to combine concurrent streams of data somehow. Sometimes you want to parallelize things to make them faster. So reactive streams are mostly used with I/O operations. So we probably read something from the network, we write something to disk, and so on and so on. And whenever there's any talk of I/O operations, error handling comes in. Right? So a big part of the reactive streams API was to safely and sanely handle errors. So we want to keep that as well. So from these characteristics that we want to keep in an implementation that is going to follow, right? So reactive stream, out of necessity, used asynchronous operations. It relied heavily on futures in the Java implementations because the runtime didn't give us any additional possibilities. This now has changed. But what we want to retain from these characteristics is the notion of back pressure. So if we have a fast producer and a slow consumer, we don't want the fast producer to overwhelm the slow consumer so that our system blows up. So we want the slow consumer to actually let know the fast producer to slow down and wait until we catch up, so that we, once again, keep our computation within bounded memory. So we want to have some error handling. So in case of errors, we want to clean up the whole pipeline nicely so there are no leftovers. The notion of completion is also quite important, so we want to be able to say that we're actually done processing the stream of data and all elements have been processed. And finally, asynchronous processing. So the notions of synchronous, asynchronous are sometimes overloaded, but what we mean here is that we want to keep the various concurrency operators that we have used before. And I think the most successful or maybe well-known implementation of the reactive approach when it comes to streaming data is Akka streams. So here is a toy example, doesn't really do anything, of Akka streams in action using the Java API. So the core of the definition of the stream is over here, right? So let's look at some of the characteristics of such a stream. And I think that's like what we very often use today in our code when we have to process a stream of data. So we create a finite stream of the first 100 numbers. Then we say that we want to emit each element every second, right? So we introduce some kind of slowdown. And then we say that we want to asynchronously map these elements. So we want to process at most 4 elements concurrently. But to do the concurrent processing, we have to use the future approach, right? So we have to create a future which does some computations in the background because we are not able to block threads. That is because we want to process a large number of elements and a large number of such mapping invocations on a small pool of threads on which Akka is using, right? So here we are using completable futures. So that is a way of actually delaying the computation. So delayed is an executor which produces things which delays everything by 5 seconds. So that is like kind of an asynchronous or future compatible sleep, let's say. And then we have the then apply async method, which is kind of like a map, but for some reasons they called it then apply async, not map, just to confuse everybody. So we are just mapping over the future to somehow further transform the result. Then we do some filtering. We can zip two streams. Sorry, we can zip two sources. So the nuts here is another source which is created using an iterator. And then we can finally, so these operations that we have done here so far, they only create a description of the stream, right? So they don't run anything. So if we run this highlighted code, the only thing that will happen is we will allocate some memory, and that's it, right? So then in the end, we have to actually run the stream. So we have to tell the runtime, the Akka runtime, which is passed over here, to actually run the stream according to the description that is passed over here. And as with everything else in Akka, we have to run it to a completable future. Okay, so that's like the status quo of how we can do these data transformations now using Akka streams. So let's see if we can actually improve it in any way and make it any better. So the tool that we will try to use to make it better is virtual threads that I introduced as part of Project Loom in Java 21. Of course, the main part of Project Loom is the introduction of the notion of virtual threads. They are very quick to create, they are lightweight to create, they are very fast to switch between, and we can easily create, here we can create 10 million of virtual threads, and we just start and stop them, so there's nothing, so we start them and then we join them, sorry. You can see that this should complete quite quickly. Yeah, so creating 10 million threads took less than 2 seconds, which is, I guess, quite fast for a JVM that isn't warmed up. But that's not the only thing that Loom introduced. So virtual threads as a construct is one thing. Another thing is that all operations on the JVM are retrofitted to actually use virtual threads. So all blocking operations, they don't suspend the underlying platform thread, but they only put aside the currently running platform thread, the currently running virtual thread. So whenever we do I/O, whenever we do any like a semaphore operation, thread.sleep, and so on, if it's run on a virtual thread, it won't block the underlying thing. It will only put aside the currently running virtual thread. And when it's once again ready for execution, it will resume. And the third thing is that the JVM now contains a runtime, which allows us to run these virtual threads efficiently. So we can run a lot of these virtual threads on a small pool of platform threads. It's exactly the same thing that Akka does behind the scenes, although Akka does it on a library level, and the JVM does it on the VM level, right? So it has this asynchronous runtime built in. And because it has this asynchronous runtime built in, we can use the nice direct syntax instead of having to use futures. But the idea is quite similar. So there's three things that Loom set out to do as described by its creators. There's three things that Loom wanted to fix, right? So the first one was that it wanted to once again bring back the possibility to use direct syntax, to use blocking code, instead of mapping, flat mapping, or then apply asyncing futures, for example. The second thing is that they wanted to fix is that futures and other future-like containers are viral. So if you are calling a method that returns a future from your method should probably return a future as well, right? You should never block on futures. That was kind of forbidden in a way because it was blocking the thread, which we should never do. And finally, the goal was to bring back meaningful stack traces. So if you throw an exception in a future, very often the stack trace you get contains only a small portion of the actual stack trace, right? Because it only contains the portion up to the latest thread switch. So these are three things that we would like to fix. Okay, so let's try to do that. So the question is, can we do the stream processing as demonstrated here in the Akka example, right? So concurrent, fast, safe, and stream processing in a blocking way using the blocking APIs that Loom gives us. So to actually implement such a blocking streaming approach, let's look at what a stream processing pipeline actually consists of, right? So first of all, we've got a number of stages. So this range, throttle, map async, filter, these are all processing stages, right, which are connected to each other, and they are combined into a pipeline using an API. So this API, in case of Akka, is quite pleasant. We have these names, which are quite meaningful, so we understand what they do. And finally, we have the runtime, which executes the pipeline. So in Akka's case, it's the actor system. So we will have, in a way, to implement all of these three things. So first of all, we will take a look into how we can communicate between those channels, right? We have between those stages. We have two stages running concurrently, and how we can communicate between them. So to do that, we will actually take inspiration from another programming language, so specifically from Go. Go isn't the most sophisticated programming language out there, or the most inventive one. It's rather basic, I guess many would say, but it did prove that communicating between lightweight threads, so Go routines in that case, using channels, is a very good way to do concurrency, right? So it's based on a theory called communicating sequential processes. So it's even based in academia, but it turned out in practice that it's useful as well. So we will try to emulate Go channels with Java, because we now also have lightweight threads, so virtual threads, which are very similar to Go routines, right? So we will need a concurrent data structure. It's going to be queue-like, so the basic operations are going to be send and receive. Our data structure will be completable, So it will be able to be closed, either saying that all elements have been processed or that there has been an error. So we need it to be interruption friendly. So we need in all the APIs that we design, we want to be able to interrupt things, right? Saying that there has been an error. Please stop doing whatever you are doing. We are just throwing the exception. So for that, we are using the thread interruption that has been also retrofitted to work with virtual threads. And of course, it needs to be fast because it's quite a basic data structure. And actually, the same thing was done in Kotlin, because Kotlin also has lightweight threads. They're called coroutines there, right? So the Kotlin team implemented such a data structure and published their design in a paper called Fast and Scalable Channels in Kotlin Coroutines. So what we did is we actually re-implemented the same algorithm in Java, and that is part of the JOX project. That's one of our open source projects on which this talk is based. So the JOX project, among other things, implements the Kotlin algorithm for implementing Go-like channels in Java. So let's see how this works. So as I said, the most basic use case is that we can create a channel with some bounded capacity. The capacity here means that we can send 16 elements to the channel, and the 17th send will block, as in block the virtual thread. So here we are sending a couple of elements, and then we say that we are done. So no more elements will be sent, and so there's no concurrency here, but this could be run on 2 threads as well. So then we can receive 4 elements, and this should, as you can see, receive these 3 elements. So nothing very surprising. Okay, so that's like the basic use case. The second characteristics is that the errors are short-circuiting our operations. So if we have a channel and we send 3 values and then an error occurs, so unlike done, which kept the values until they were received, if an error is signaled, everything is short-circuiting, and we can see that when we try to receive, we only get the error back. And finally, sorry, this is the third. And finally, it's a feature that's very useful when we want to do concurrency on channels. So let's say we have 2 channels, both of capacity 16, and we want to receive from those channels, but we don't know which channel is ready for receiving. And that's where when we can use the select operation. So that is also inspired by the feature in the Go language, where you can select from a number of channels, right? So here we select exactly one value, either from the first channel or from the second channel. Right? So if there's a value in the second channel, it will be received, and the first channel will be left intact, and vice versa. So here in the example, we start a thread. We start a virtual thread. So it sends a number of elements to the channel, then it sleeps. So we start 2 of those threads sending various numbers to those 2 channels. So when we run it, we should see some kind of interleaving between those two channels. So what we have implemented here is kind of a merge between those 2 channels using the select operation. So that is going to be one of our basic building blocks. And one important thing is how fast are these channels. So as I said, the Kotlin team really focused on performance. So here's just one benchmark. Of course, you can do a number of different benchmarks. In this particular benchmark, we have 10K thread or coroutine or goroutine pairs, which are connected by channels. So we have 10K pairs, and each pair sends 100K values from the first to the second channel. So it's some kind of simulating some parallel processing. All of these implementations are fast. So here we compare the JOX implementation, the Kotlin implementation, and just using Java concurrent queue directly. They're all more or less the same. So these are nanoseconds. That's the average number of nanoseconds to process a single element. Go is still a bit faster. But again, it might only be a single benchmark. But most importantly, these differences are not really big, and all of these implementations are really fast. Okay, so now we've got a basic building block of how we can communicate to concurrently running some data processing stages. But now, how about building a high-level API on top of that? And well, our first approach to this might be to actually extend the channel with some operations such as map. So here I cannot modify the channel class directly, so I created a simple wrapper called rich channel just to demonstrate things. So the way we could do things is, we could have a channel, and then we could have a .map operation, which would return a new channel which would contain values that have been mapped using this function, right? So the way we could implement it is, well, we have to return a new channel, right? But this channel needs to have all these elements from this old channel, but transformed. So we need to run some kind of a background thread, which actually receives value from the original channel, right? Applies the transformation function and sends it back to the new channel. So each map invocation over here actually starts a new virtual thread which performs the mapping. And that's what is implemented in the rich channel function over here. So the map, we create a new channel which has some kind of capacity, and then we return this channel over here. And we start, as a side effect of map, we start a virtual thread, which in an infinite loop, receives from the channel and from the source channel and sends the mapped values to the result channel. And this works. It has some downsides, but let's first see if it actually works. So yeah, so we send 2 values over here, and we have a series of maps. So this should, just return to 90. So maybe it would be more interesting if these values are different. But yeah, this actually gives different results. So when we run this, we start 4 virtual threads. And this way, we could also, implement all of these other high-level operations as we have as we have seen in this example. So we could implement throttle, we could implement filter, and each of these would actually start a new virtual thread in the background. Well, but this would be, sorry, I lost. Yeah, this would actually be a bit wasteful, right? Because you don't really need to run such simple mapping operations in a separate virtual thread. It's a very lightweight operation, right? So there's too much concurrency in this approach. So we could probably do better. So for that, so far we have stayed in Java. I will have to switch to Scala. Let me explain why. So this whole research into how we can utilize blocking operations and Loom to perform streaming operations and structured concurrency, it all started as a Scala project called Ox. And now I'm slowly moving so after a year of experimentation, I'm slowly moving these parts that have worked in the Scala implementation to the Java implementation called JOX, which we have seen. I didn't move the stream processing yet, so we are now going to look at the Scala one, but it's coming in a Java version as well. So Ox is a library which aims to implement structured concurrency for safety, and in fact, the streaming processing that we are using utilizes structured concurrency to make sure that everything is nicely that the error handling works properly, but it also offers a high-level streaming API on top of channels, which we will now examine. Okay, so let's go over here. So the key insight here is that, well, before with the mapping over channels, what we had to do is we had to run too much virtual threads. So we have kind of to take a step back and actually go back to the idea of first creating a description of how our streaming pipeline should work, and only later running it. This will allow us to actually defer the decisions when to start the new background processing threads to a later stage. Right? So that's where flow comes in. And once again, this is inspired by a very similar thing that has been done in Kotlin. There is Kotlin flow as well, serves a similar purpose. The API is a bit different, but we have to adapt to the language and platform that we're actually using. So here we are first creating a flow which will a finite flow which emits 7 or 8 values. Then we do a dot map, dot filter. So these are all operations that you might know, from collections, from the JavaStream API, and so on. Then we have some stages that you might know from akka streams, for example, like intersperse, so putting elements in between each 2 consecutive elements, like map stateful. So here the map stateful is computing the running total of the values that we have seen so far. That's the initial state, and that's the value that we are emitting downstream, so the updated running total, and that's the new state that we will use for the next value. Just as with akka streams, when we run this code, it will only create a description of the pipeline that we want to run, and we then have to run it, right? So it's like a collector. So then here we run it to a list, and then we can print line the result. So we can run this, and we get some numbers. So if you are curious, you can verify if these numbers actually match these transformations, but they do. Okay, so that's not that interesting, right? Just some kind of high-level API for transforming values. Of course, it gets interesting when we introduce concurrency. As a second example, here's a flow which emits some value, tick 1 every 1 second, and another flow emits a value every 2 seconds. And then we have some operations like merge, for example, which merges these 2 flows together. So how this works? When you actually run, right? Because once again, f1.merge f2, it's just a description. We have to run it. So once we run it, what happens is we create a virtual thread which runs the first flow. Then we create a second virtual thread which runs the second flow, and they all emit values onto channels, the same channels that we have seen before. And on the main thread, we use the select operation that we have seen to take values from whichever channel is actually ready for, and whichever channel has some values in it. So that's how we can merge the operations. And what's also quite important is how we propagate errors. So if there's an exception, for example, in this flow after some time, the runtime will catch it, and it will signal an error on the channel, right? So here we are using the fact that channels are able to propagate error in an out-of-bound way, right? So it's not like a regular element. When we signal an error, the whole channel will be cleared, and only the channel will be signaled downstream. And then the select will also report the error as fast as it is reported. So we can just run it to see if it works as expected. So we get twice as many tick 1s as tick 2s. In a similar way, we can implement other concurrent operators, such as zip, right? So zip, very similar idea. It runs the first flow in the background, runs the second, and then combines them. But here we just wait for both values to be available. So the whole idea here is to hide as much concurrency as possible behind an API. You don't want to do concurrency by yourself because it usually ends up badly. So if we can get away with declarative concurrency, such as these operators, then we are usually quite safe. Now let's take a look at how we can actually implement some blocking operations, right? Because that's the interesting part as well. We can that actually comes quite naturally because we don't have to do anything special. We can just, because everything is based on virtual threads, we can just do the blocking operations. We don't need any kind of special APIs, any features, and so on and so on. So here we've got a flow which reads chunks of bytes from the given input stream. parses these bytes as UTF-8 lines, and then we do a parallel map. So we say that we want to have at most 4 invocations, at most 4 concurrent invocations of this given function. So for each line that we read, so it's like a data element from this file, we want to send an HTTP request, for example, right? And this is implement, some using HTTP client or something like that. And it's blocking, right? And it's totally fine because each of these threads that we are going to create here is actually backed by a virtual thread. Error handling is done using structured concurrency, which means that if any of these fails with an exception, there's like a structured concurrency block around. So the exception once again will be propagated to the outside of this scope. But before it's propagated, all other threads that are still running and transforming the data will be interrupted, and we will wait until they complete. Right. So this way we ensure that everything will be left in a clean state. So another thing that Loom wanted to fix is preserving the context and exception handling. So here we have a flow which every second will for the first 3 elements it will just emit the numbers, and then it will throw a runtime exception, right? So an error. And here we have another flow that just works. So we merge those 2 flows together, so that's done so that you can see what happens if there's some concurrency involved. And of course, this should fail. This merge should fail as well, because the first flow fails. And when we run this, so this will run for like 3 seconds. And yeah, then we get the exception. Where's the stack trace? And you can see that the entire context is preserved. So we have 2 exceptions here, because maybe let's make this a bit smaller. Because we have first the top level, the merge over here, which is pointed from this exception, right? So the merge over here is referenced in the exception, but also the original exception. This one over here is present as a cause as well, right? So we get the full information of how this actually, where this exception actually came from, which is in contrast to other approaches like the Akka streams and the other reactive ones, which are based on futures. So we are able to retain this characteristic of Loom as well. And finally, I guess one quite important part is how we can actually integrate, with any other technology, any other component that we have that produces streaming data, and that is very often done using channels. So here's a quick demo of how we can create flows from channels and create and run flows into channels, right? So we create a channel, a buffered channel. We send some elements to that channel, then we say it's done. And then we create a flow which reads, which will, when run, will read elements or receive elements from that channel, right? Then we apply a number of transformations, very similar to what we did in the rich channel example. However, here, when we run this, all of these 3 elements, all of these 3 transformations will run on a single virtual thread, right? Because we first create a description of how to transform the data and only later run it, right? So this will run on a single virtual thread. When we .run to channel, we will start a background thread, which actually every value that is emitted by the flow will be written to the channel. And here in the flow, we can introduce buffers. We can introduce asynchronous boundaries with async, for example, and do any kind of other transformations that we do with flows. Let's see if it works. Yeah, so we filtered out some values, so we got 2 values over here and then a done value, right? So all these, both the error signals and the completion signals are all preserved and transferred through these flows. Okay, and finally, so channels are like a kind of a technical way to communicate between concurrently running processes. Now, the most flexible way of creating flows is actually using this flow using emit constructor. So emit is used to send values downstream. Okay. So, for example, if we want to integrate with Kafka or with Redis or any other queue out there, what we can do is we can, so that's the body of the flow that will actually be run when the flow is run itself, right? So when the flow is run, what we need to do is we need to connect like to our other system. So we don't see it here, but we could, for example, connect to Kafka, and Kafka could produce. The way the Kafka API works is it has separate ways of signaling when data is received and when exceptions occur, right? So we can have two channels, one for data and one for errors. Yeah, so what we would do here is we would have somehow to connect to Kafka using data and errors. So that's like a detail that we omit. But then what we do is we would, in a forever loop, so it's like a while true loop, we would select either from the errors channel or from the data channel. The errors channel has precedence, right? So if there's an exception, it's always taken first. And then, if we received a data element, we can also, do arbitrary control for over here. So we can emit this element downstream. So this emit element, this emit invocation, what it does is it sends the value downstream, and it will actually block until that value is processed all the way downstream, right? Signaling errors when implementing such custom stages is trivial because we just throw exceptions, and that's it. So we can look at the implementation of such a flow, and it's actually quite simple. So that's the gist of it. So the flow itself doesn't really have anything special. It just contains a reference to the last flow stage, plus a bunch of methods like map, filter, and so on, which are not shown here. But the flow stage itself has a single method run. The run method, it's invoked when we when we actually run the flow, and it's given a single value, so it's a way to send values downstream. And sending values downstream has a single apply method with which we can send the values. So the design is quite simple. It's quite trivial to write your own flow stages, right? A typical flow stage, like a merge flow stage, let's say, what it does is it would run the two flows that it's given in virtual threads in the background, and when then combine their values using channels. And when this happens, it would use the emit to send values downstream. So emit has one usage restriction. It's not thread safe, so it should never be passed to other threads. It should only be used on the thread that is calling run. That's why we have to use channels to communicate between threads. Completion here is also very simple to signal. So when run completes, we know that our stream is done, so we can do any cleanup logic, like in finally, for example. So it's a Java feature that we can simply use. And signaling errors, once again, very simple. We just throw exceptions. So using that approach, that's the re-implementation of the same example that we've seen in Akka before, right? So we maybe almost the same, because I think there was a finite range here. We had just as a flow of natural numbers. Yeah, but we have the throttle API as before. We have the map par. So maybe you remember that in the Akka example, we had to use futures. We had to use some executors for delays. Here, we can just use blocking operations because we are using virtual threads, right? So we can do threads.sleep. We don't have to do any maps, any flat maps. We can just do normal Java, Scala code, whatever. Filtering, zipping, which runs these two streams concurrently. So the re-implementation of the Akka example using virtual threads, I think, turned out quite straightforward. The missing component, I guess, that I didn't mention is the runtime. In case of Akka, you needed a runtime to actually manage scheduling those futures onto the small thread pool that is running things behind. Here we don't really need a runtime. We have Java, which is our runtime, and it's Java and the JVM that actually manages the scheduling of virtual threads onto the pool of platform threads. So we get it kind of for free. But this greatly simplifies things that we don't have to introduce the additional runtime component. One important notice that I didn't yet mention about flows is how data actually flows, right? So maybe if we go back to the last demo over here, or maybe let's go over here. So here, yeah. So once we receive a value from a channel, and it's emitted downstream, these values are emitted one by one, right? So this flow dot from source, it will receive a value from the channel. It will call the emit, so it's processed downstream. So the emit will then go to the map, the second map, the filter, and it will be sent to the outgoing channel, which is the result over here. And only then we will go back to receiving the next value from the channel, mapping, filtering, sending, and so on, right? So this is all quite a simple mental model of how these flows actually operate and when these values are processed. Okay, so I've got one closing slide where I wanted to share some things about our company. So Software Mill is the company I work for. They also sponsor the open source projects such as JOX, OX, and different ones as well. We are a software development company. We try to help our clients solve their problems using software. We focus on the back end, using various languages, starting from Scala through Java, Kotlin, Rust, to TypeScript, and various other components that help us, especially Kafka. Yeah, we do a bunch of open source things. We are hiring if you would want to check us out. We have a very nice technical blog, which I think has very interesting content by our engineers. Okay, so that's about Software Mill. So now let's do a quick summary of the various pros and cons of the various streaming approaches. So first of all, we've got the Akka or the reactive APIs, right? So there's a bunch of these implementations, but they all share similar traits. So they have a very versatile API. So there's a lot of these combinators that you can use to actually build out your pipelines. Also, the implementation is quite battle-proven, so it has been used in production in many systems. So it will probably work just fine. However, it's quite difficult to create new stages. So if there is no combinator or operator that meets your needs, actually writing your own one is not that easy. So there's this Graph API, which might be a bit scary. Then we have the problem of colored functions, which I mentioned, the virality of futures, right? So when you work with Akka streams or other reactive implementations, you usually have to work with futures all the way through. So your entire code is based on futures. So this is somewhat fixed by Kotlin. So it's much easier to create new stages. The Kotlin implementation is very fast as well. The syntax is nicer because we get these suspended functions, but they are still colored, right? So it's not like you don't have any of these problems as with futures. Just the coloring is or the marking of the future of the methods that are asynchronous is moved from the type to an annotation of the method. Stack traces is still a problem, and the runtime is still there. Now in the OX or the JOX case, the performance is still there because we are using the same implementation as in Kotlin. It's very easy to create new stages, as I hopefully have shown you. We don't have any colored functions, right? We can just write blocking code as we want to. Stack traces are very nice. They retain the whole context. and we don't need an additional runtime. We also have two APIs to define streams, right? One is the functional, let's say one, based on flows, the high-level one, but sometimes we have to fall back to an API based on channels. It's not always obvious, so it's good to have this choice, but it's not always obvious when to choose which. And of course, Ox is a brand new library, so there's no integrations. It's not optimized. It's in development. So while I, of course, encourage you to try it out and give us feedback, it's probably not exactly production ready yet. Maybe next week. Okay. What's worth mentioning that all of these implementations, so Kotlin, Akka, and the Ox one, are reactive, right? So they are back pressured. If we block a thread in our flow in Ox, this will actually bubble up all the way up, filling out the buffers that we have. So there's back pressuring. We can do error handling, as I have shown, and signal completion as well. Yeah, so that's I think all I had. Please take a look at our both of these projects. If you have found them interesting, leave a star. If not, don't leave a star, so that we will know that people actually don't like it. But yeah, these actually help to for us to see if there's interest in a given approach or not. We are running a weekly Scala newsletter if you would be interested in Scala and functional programming. And yeah, I think direct side streaming in a blocking way is definitely possible, thanks to the advancements of Java. We just have to develop our ecosystem around it a little bit to make it production ready. So I'm here for the rest of the day. If you would like to talk, I would be happy to take any questions later because we are out of time. So yeah, and with that, thank you very much.